Again, I'm recording this, and I want to start off with one concept, and that is the concept of of what's the difference between a theory, which we've already discussed, but obviously a lot of people don't get. A theory, a law, and, bless you, facts. A lot of people will argue that facts are what people say they are. That's not true. That's unfortunate that people have that attitude. In our world, the world that you're growing into, facts are what you read on the internet. Facts for you are what somebody tells you. Facts are what some Russian in Russia or some Chinese person in China or somebody on a website on the other side of the planet says the facts are, and all of a sudden you're believing them and you're moving on making decisions based on that. Those are not facts. All right? Facts are indisputable. They are common among us. If it's a fact, you see it, I see it, there's no different way of looking at it. Those things, when you can look at something and look at it two different ways, we call that opinion. Do you understand that? Opinions, there's no right or wrong opinion, right? Because opinions, at least in the short term, opinions are subjective. You think it's good, I think it's bad. You think it's hot, I think it's cold. It doesn't matter, because we're both right. But facts, the fact that it's 70 degrees, the fact that it's rotten, or that the fact that it has a lot of sugar in it, that is a fact, and that cannot be denied. To deny that is to deny reality. So facts are observed. They are observed, not translated. We're not given any kind of subjective measurement. A law is when we find a pattern in what we observe. That is a law. I'm sitting under a tree and an apple falls on my head. That's an observation. Every time I throw something up, it comes down. That's a what? It's a law. It's a pattern. A law is just a pattern. Then the theory is an explanation of that pattern. It's an explanation of that pattern. That's based on experimentation. And the scientific method. Don't ever tell me that it's just a theory. Do theories change? Heck yeah. Because that's part of the scientific method. We expect to change things. Science is about what we understand things to be right now. Science is not about some kind of absolute truth. We hope we're getting close to the absolute truth, but that's not the point, is it? The point is a theory that explains what we observe and that helps us predict something that might happen in the future. That's all. So a theory, not only does it explain what we've observed in the past, but then what? It should predict the future. And how well it predicts the future makes it a good or bad theory. And if it's bad enough, what do? Throw it out. I got no dog in this fight, man. It's a theory. If it's wrong, get it out of here. But until it's proven wrong, we accept it, we keep going, we use it because it's helpful. Right? If it's not helpful, get rid of it. This is about what works. This thing that we're talking about is called science. That is science. It's the stuff that gives you everything you're talking about. Everything you do in your life, most of it, comes from science. So to pick and choose what you will accept and what you will not accept because of science it's a little hypocritical, right? So you have to understand that these are facts. This is how things work in science. It doesn't mean that what you believe is wrong. It doesn't mean that you can't believe that there's some other explanation we just don't know yet. Believe that all you want, guys. All right? Your personal belief has nothing to do with this. Are we clear? This is just about what works. So we'll be talking, move forward. Science. So what I'm about to tell you, this story I'm going to tell you is a story. It's based on, there are books and books in libraries full of explanations and experiments and data and analysis and theories, and there's numerous competing theories. No one's chosen a right one. One theory that a lot of people accept for right now, and some people are questioning though, is this whole Big Bang thing, right? Then there's dark matter, and then there's all kinds of things. But we can't observe things, right? We can see things through telescopes. And based on what we see through telescopes, we can infer some things. This is some things where we can look at. And one of the things we look at is that when we talk about the universe, we can identify in a galaxy things we call nebula. And nebula are these giant clouds in space, giant cosmic dust clouds. Cosmic, meaning they're in space, dust, clouds. Stardust. These cosmic clouds are suns that were born and died and blew up in a supernova, and they threw out all kinds of matter, all kinds of atoms, and they're just sitting there in space. And what do these cosmic dust clouds do over time? What do they do over time? Yeah. They start to do what? Go ahead. That's right. They start to group together. They start to pull on each other. It's called gravity. So these things start to pull on themselves. And you form little ones and big ones. And then finally, over time, you form really, really super giant ones. And the super giant ones are really big. Really big. And one of those supergiant ones could be a what? It could be a galaxy in the beginning, yeah, but it could be, well, all right, I could see that as being a black hole as well. Well, it turns out that some of these, and of course, you can have this going on, can't you? Rings. What planet would have rings? Saturn, and you can have Jupiter out here, a really big one. But what's interesting is that this big one, what is this big one in the center here? The sun. The sun. And the sun was formed by the same cosmic dust that forms the rest of the planets, okay? And what's interesting is that the sun is, I don't know if you know this, but the Earth is 100,000 times smaller than the sun. You can fit 100,000 Earths in the sun. Isn't that crazy? Everything you know how long it takes you to cross from here to China? You think that's pretty far? Could you walk it? You probably could, but it'd take you a long time, right? Huh? Well, you can get on a boat and walk on a boat, right? Right? You can wait till the ocean's frozen and cross the Pacific. But except for the ocean, we all agree. Actually, I'm way off. I looked it up. Man, I'm wrong. 1.3 million Earths would fill up in the sun. Fix that. 1.3 million Earths. Isn't that crazy? You live on a planet that you and I agree, I think it's pretty big too. You and I think it's pretty big. But if this is Earth, 1.3 million of these fit inside that sun. That's how small we are compared to the sun. What? How big is the sun? 1.3 million times the sun. Think of the Earth, multiply it. Can you imagine? It's hard to imagine, right? But take this planet, the whole planet, the atmosphere, all the land, everything, multiplied times 1.3 million, and that's how big the sun is. That's pretty daggone big. You agree?
Yeah.
So that's how much stardust went into this thing. And it was so big, it had so much gravity that it pushed atoms together. It took one atom that we learned about, another atom, and it pushed them together, and you got something called fusion. And in France, we're making one of these fusion generators now. And everybody's investing in it. We're hoping it works, because if it works, then we'll have cheap, clean energy for the planet. So this fusion is what powers the sun, is that its gravity makes these atoms come together and takes two atoms and makes them into one. And what it's doing is taking helium or hydrogen atoms and then pushing them into and making new atoms inside it. And when it does that, it releases a tremendous amount of heat, a tremendous amount of light, a tremendous amount of energy in general. And it goes out from the sun, doesn't it? Who knows that the sun releases rays out, right? And all the way around, and it goes and hits our Earth and gives the plants their energy that allows them to make sugar and blah blah blah, right? We're all okay with that idea? Yeah. Well, our Earth and the other planets were too small for that to happen, but they were whizzing by. They were whizzing by in every direction, moving this way and that. And what happened? Who can tell me what happened? Around 5 after 12 on the giant historical clock. Yeah.
It collided.
What collided with the Earth?
Something the size of Mars.
That's right. Some planet the size of Mars collided with the Earth. We know that. I'm not going to get into the observations that we have. I'm not going to get into the laws that drive it, and I'm not going to get into the theories behind it. But one of the theories that we've pretty much accepted as standard for right now, could change tomorrow, right? But right now what we know is that there was this Earth-size, kind of something a little smaller than the Earth we live on now. And there's a planet about the size of Mars, and it came and hit Earth, broke it into continental shelves, right? Into continental plates, and it broke the Earth's crust that was cooling off. At that point, the Earth was cooling off, and part of it, and give it some time, it came over here, and what left after the collision was one bigger Earth. The Earth was bigger now, and then it had what? Another little sphere. What's this yellow one? The moon. So the moon and the Earth is what's left over after two planets collided. About 5 minutes after 12 on the Earth's history. So in the end, had this Earth-sized planet, you had this moon and they kind of orbit each other, right? And then here we have this giant thing that we call the sun that gives us all our energy. And then we had all these other planets out here, right? We had Saturn with its rings. And you had Jupiter, the biggest of the gas giants. And you had Mercury, which is a small planet, and Venus. And then you have Mars out here. It's a little bit smaller than... Of course, this is all badly drawn, right? Everybody understand that, right? Mm-hmm. So now we used to have 9, now we all agree that we have something like 8, right? Everybody okay with that? And then the planet was kind of, this part here we call Earth, that's our home. But that's not the whole story, is it? That's the Earth started, what was it like on earlier? What were the conditions that were present after the Earth started to cool? What were the conditions after the water had condensed into oceans and lakes? And were they different from what they are today? Right after it hit, it's revolving around the sun. It's doing its... What's going on this planet that we call Earth? What was the atmosphere like? All right, it was thick. I like that word, thick. What was in it? What was it composed of? Was there nitrogen? N2 gas? No. So today we have nitrogen, right? Today we have our atmosphere is mostly nitrogen. I don't know if you knew that, but if you didn't, you should write it down. A good 70+% is nitrogen today. So today, let me use a different color. Today, our Earth has about 70+% N2 gas. There was none then. What else do you know about the atmosphere of the early Earth? Somebody want to say? Wait, say that again. Right, so it was thick and cloudy. I'll go cloudy. I like that. It was so cloudy that it was hard for the Earth's the sunlight to enter it. Very cloudy. Okay, I can go with that. There was water, right? H2O. There was water in the early Earth. What was the atmosphere like? What is it not like now? Let me rephrase it. Let me ask a different question. What is the atmosphere like today?
He said that the sky wasn't blue before.
Right, the sky wasn't blue earlier.
It was a reddish color.
It was a reddish color, is right.
Yeah.
So, but I guess I'm still not hearing the answer that I'm looking for, and that answer is, what is let me pause this. So our early atmosphere is over here. And our present atmosphere is here. Let's write down our present atmosphere. What's our atmosphere like today? Our atmosphere like today is about 70, let's just go ahead and say 78% nitrogen, all right? N2 gas, so in its gas form. Today we have oxygen at about 21%. Yikes. And that's O2 gas. So about 21% is O2 gas. So that's oxygen gas, the gas we breathe. And what do you think the CO2 is, the carbon dioxide today? Carbon dioxide. How much is the Earth's carbon dioxide?
1%.
I heard 1%. What else?
Wait, that's like this.
There are different numbers.
Like 15.
There are different numbers from different sources, but come on, give me a guess. Give me a guess.
Say one.
I say 15.
17.
12.
8. 17.
Girl, I'm guessing.
Say 17%, okay.
8.
8, 7, 1. Anybody else?
12.
12. Yeah.
If that's 90,
That's 99 right there.
Right.
Yeah, that's right.
I been said that.
Is it
I
0.1?
said 1.
So it's 99%. So where are we? So we know it's not more than 1%.
It's 1% or lower.
It's not 1%.
So point
0.003.
All right. So carbon dioxide, which is very important. You agree it's a very important gas, right?
yeah.
All right. So this very important gas is 0.036% of our atmosphere.
0.03.
And all the rest of it is what we call, and carbon dioxide too, is we call these trace gases. There's all kinds of other gases, right? So trace gas, what are some of the trace gases that we find We find things like neon at 0.0018, helium, methane, hydrogen is, guess what hydrogen is? 0.00005% hydrogen. Close, but no cigar. Ozone is even smaller amount. All right, so we have a lot of trace gases. There's a lot of them. All right. It's like, all right. So, but what was the early atmosphere then like? What was the early atmosphere? What was the composition of the early atmosphere? Somebody from the video. Somebody tell me. Yeah, go ahead.
This is a guess because I heard they had hydrogen sulfide.
It's filled with CO2 and hydrogen.
Hydrogen sulfide is correct. All right, so hydrogen sulfide is certainly, let me pause this again. So we want to find out what the atmosphere of the early Earth was like. Put it away. And where would we go to find out what the atmosphere of the early Earth was like? The video told you, right? So where might we look for the composition of the early Earth? Yeah.
What's in the beginning of the clock?
Okay, but there's no real clock, right? The clock is just a pretend thing. Where would we physically go and say, okay, what was the atmosphere like 2.5 billion years ago? Or 3.5 billion years ago?
Place 2.5 billion years ago.
Right, so where place would be frozen in time 2.5 billion years?
Is that a?
That's a fantastic guess. I love that. Last, you're thinking the cold, right? Frozen, right? That's excellent. Excellent thinking. It's actually Greenland is the answer, but you're close. And the Greenland is because there's rocks on the Greenland that are 3.5 billion years old.
Wait, you're not right there.
They were formed early on. So Greenland is one place. So it's the first question I'm going to write here is where, and I'm going to put Greenland.
I have a question.
Hey, you want to know something else? And we can look at, we can test, and there are rocks that are 3.5 billion years old. And I'm not going to go into the radioactive decay and how we know it's 3.5 billion years old. Just know that they're 3.5 billion years old. So that's in Greenland, and we can test the rocks, and we can come up with some. Now let me ask you something. What if there was no life on Earth? Because what changed the atmosphere? Well, let me go back and do this. Let me write this down. The 3.5 billion years ago, there was what? So sulfur dioxide in the air. There was from volcanoes and such. CO2 was about 90+% of the Earth's atmosphere, not nitrogen. Nitrogen gas, N2 gas was, maybe made 1%, approximately 1% of the atmosphere of the Earth, in ancient Earth. And there was 0% oxygen. The stuff we breathe in all the time, the stuff that makes up 20+% of our atmosphere today, there was 0%. 0%, that's intense. And water back then, earlier, there was some water, maybe it was, I don't know, anywhere from 0.1 or something like that percent. Then things started happening, so that was the earlier, this is the atmosphere composition. If this was true, and what changed it, let me ask you this question. What made the change from this composition, is this hospitable to us? Could we live in this? No. What allowed light to come, I messed up what I'm saying here. What changed this into this? What made oxygen, free oxygen, O2, what made the nitrogen out here? What got rid, what allowed this to go into this? There's two answers to this and we'll have to talk about it, yeah?
I know in the video they was talking about like that cyan bacteria.
That's right, excellent. It was life that did it, Cyanobacteria. cyanobacteria. Now, it wasn't cyanobacteria back then. That's what we know does the same process today. Maybe they were cyanobacteria. We don't really know what they were. But we know they were this. We know they were prokaryote. That's according to theory, based on observations and laws. They don't have nuclei, right? They do. The reason we know this is we can find examples of these creatures right now, right? You saw in the video, down in the mines, at the bottom of the ocean, and we can find these things are still doing this stuff today. So it's not like they've gone away anywhere, they're still here. And so what we find is that these cyanobacteria, what they took is they took all this CO2 over billions of years, right? What's interesting is they took that CO2 and made what?
Oxygen.
Made oxygen, that's right. They took that CO2 and they made oxygen out of it.
That's the present.
That's today. So that's what moved that CO2, changed it into something that was something that we could use here. It also released the nitrogen gas that was in the nitrates, because originally they were also in the liquid, in the water, there was NO3, all right, and NO2. These are called nitrites and nitrates. We produce this, you produce this, you change this into urea and you pee it out. But when you process this, you make this. But we take that nitrogen, that nitrate, and that nitrite, and those bacteria change these nitrates and nitrites in the water into what? Into the biggest gas component of our atmosphere today, into nitrogen gas. If it wasn't for these bacteria, that, by the way, for most of that clock, right, for most of the history, and remember, what does that clock represent? The history of the world, 3.5 billion divided by 12. And the history of that clock, the history of the earth, most of the time on that clock this earth was ruled by, not dinosaurs, not humans, but bacteria, prokaryotes. Yeah.
So I got a question, but it's kind of going back. So for number one, could you have said it represents the Earth's history over the span of one day?
The Earth's history, yeah, over the span of one day. You could have. But that would have been a correct answer. What I would love for you to say, though, is that, and write it down, I'm giving you the answer, is the history of the Earth divided by 12.
Or 3.5 billion.
With 3.5 billion divided by 12. That's what's key here. If you're sleeping right now, and there's two of you in the room right now that's sleeping, I don't understand why, because neither one of you have A's. So you need to sit up and pay attention, please. If you're sick, dears, go to the office. You cannot sleep in this class. You can't lay your head down. I don't want to say any names. I'm recording this. Oh, God. Trayvon, please sit up straight. Pay attention to what's going on. Or go to the office. It's not a problem for me. All right. So prokaryotes, cyanobacteria, prokaryotes, we know this from fossil evidence. Like, what kind of fossil evidence? Does anybody remember? We know this from microfossils.
Oh, that was on, you gave us a hint on that paper.
Yeah, I gave you the hint on that paper, that's right. And microfossils are these little tiny indentations. You have a rock, and when you look at with the microscope, you see these tiny little indentations. And these bacteria, because of how they do what they do, they form these kind of layers, don't they? Don't they form these layers of dirt and slime, and then they move up to the surface, and more dirt and slime, right? Do you remember those? And they end up looking something like, kind of like this. Don't they look something like that in the ocean? And we can see them even today. Right now, they're still doing it.
Yeah.
You remember those things? Bacteria, the cyanobacteria. In Australia, they showed it to you, right? And so these are just packed full of these layers and layers and layers of these microfossils. And we can see these. We can go back in Greenland and other places, and we can see the exact same kind of indentations, the exact same kind of structures. So this is part of the evidence that we have that the planet was inhabited by microorganisms for most of that clock's time. Is that clear? And we can measure these. We know how fast these are made. And because we can measure them and we know how deeply they're buried in the earth, we can tell more or less what time they are. Plus, on top of that, radioactive decay data. All right, so those are microfossils, and those are prokaryotes and cyanobacteria. Now, moving forward, there's some other evidence that helps support our idea about our theory, right, about the composition of the Earth. Well, not only do we have microfossils that tell us some information, we also have rocks that have trapped gases. We can go to Greenland, and we have these rock layers, and within these rock layers, we have these bubbles. They're trapped. The gases are trapped in these. We've drilled in and stuck a needle into this layer, sucked out the gas, and guess what?
There's the bacteria.
Well, I wish, no. But in the composition of the gas in there is exactly what we thought it was 3 billion, 2 billion years ago. The composition of the gas, when we look at the gas, we can see there's sulfur dioxide, a lot of carbon dioxide, not a lot of oxygen, none at all. So a little bit of water. We know that that's true. Okay? So that's interesting. And we know that over time, cyanobacteria change the atmosphere. But interestingly, we can ask ourselves, well, what if there was no life on Earth? Could we go to somewhere? Could we go somewhere where there's no life, but the conditions should have been almost the same as it was on Earth? Weren't all the planets made the same way? Wasn't the same cloud that made all the different planets? Ideally, yeah, theoretically, right? According to our theory, that's true, right? That's our theory. According to our theory, that's true. So then the question to you is this: where could we go where we could look and see what the early atmosphere was like before life changed the planet? Yeah.
Volcanoes.
Volcanoes are a good source, possibly. There's some information we can get from volcanoes, that's true. But where can we go and say, okay, that's the atmosphere, let's take that atmosphere and test it. That's what it would be like if there was no life on Earth. Yeah. Mars. Or Venus. Those are our two closest neighbors. The gas giants are too ridiculously big, and they're mostly gases, so that's not really going to be very helpful. But we can look at Mars and Venus. And let's take a look at Mars and Venus real quick. Let's make a table. And you see why I wanted you to watch that movie and pay attention. And let's compare it to Earth. According to our theory, what would our hypothesis be as to the composition of Mars and Venus? Would it be the same as Earth today?
No.
No, it wouldn't be. It'd be a little different. Because it would be without life, right? Theoretically, life did not exist on these planets. So, what gases would we be interested in comparing? Anybody want to tell me? How about carbon dioxide? Is that a good one?
Yes.
Oxygen would be a good one. What about nitrogen? And what other one? How about water, H2O? All right, before life on Earth. Okay, so Venus has, and we look at Venus, and we have the surface pressure is ridiculous. I'm not going to write it down, but Venus's surface pressure is 100,000 millibars.
What are the millibars?
Let's just say our atmosphere, our surface pressure is 1,000.
So that
Our atmosphere is 1,000. On Venus, if you went to Venus, you'd feel 100,000 times the pressure. You get crushed like a can, empty can, like, right? 100,000 times the pressure. That's a big deal. On Mars, it's only 6 millibars, so there's no pressure. So your gas would, the nitrogen in your bloodstream would come out and bubble out and you'd boil to
So
death.
you'd be like, oh.
Right? So you wouldn't, there's not enough pressure on Mars. If you went from Earth's atmosphere right into Mars pressure, you just go and blow and just boil.
So like,
Yeah, not out of heat, but out as the gases come out of your solution.
is that why people don't travel to Mars or Venus?
No, that's the reason it's hard to get there. We would go there with suits, right? We would create our own pressure. Just like we can go underwater. We can go underwater, even though there's a lot of pressure, because we have suits that allow us to do that, right? All right, so, but looking on, there's reasons why that's important, the pressure on the 3 planets, but let's take a look at the CO2 on Venus. What do you think the CO2 on Venus? On Earth, we know it's about 0.03%. About. Nitrogen, we know is about 78%. There's argon's about 1%, but oxygen is 21%. Oops, I messed these up, didn't I? I said it right, but I wrote it wrong in order. Oxygen was 21%, right? And nitrogen was 78%. You need to know these percentages, by the way. And water on Earth today, guess the percentage?
0.07.
Is that 0.72? No, that's-
I got a question. What you say 78 was nitrogen?
Nitrogen is 78%. You said 8, and I just wrote it. All right, 0.1% water. All the water on the planet is only 0.1%.
How is
It's
that?
only 0.1% of water in the atmosphere, rather.
Oh, okay. 'Cause I was thinking
In the atmosphere.
30% water, so how is it going to be?
The surface of the Earth is 70% water, but the surface of the Earth is a very thin sliver of the entire Earth. So if you can imagine everything on the surface, everything you know, think of the planet as being an apple. Peel the apple with a nice thin peel. The peel is where we live. All the oceans and mountains and air and you and me and all our cities are on the peel. The rest of the Earth is under our feet. It's molten magma and solid continental plates and etc. So we live on a very, very tiny, tiny place. A tiny place on a tiny place in a tiny solar system in a medium-sized galaxy in a very large universe. We're very small. Now you can go home and have nightmares. All right, so anyways, so Venus, as you look at Venus, its CO2 is what? Do you think higher or lower?
High.
Very high. It's actually greater than 98%. And what Carl Sagan, have you ever heard of Carl Sagan? Probably not. But Carl Sagan was the first person to do the cosmos. A great astronomer and physicist. Carl Sagan,
Wait, they say 79, 80?
98% is what this says.
That's a great
Oh.
It's greater than 98%. Sorry, I'm messy here. So oxygen, it turns out on Venus, there's 0.0%. Carl Sagan described what happened to Venus as something called the runaway greenhouse effect. And what he said is that as volcanoes kept erupting and releasing CO2, releasing these gases that hold in heat, Venus became hotter and hotter and hotter until today the surface of Venus is extremely hot, too hot for you to live on, too hot for you, even if there was oxygen, it would be too hot for you to live on. So hot that water cannot exist in gas or solid form. And so it vaporized and water left that planet. There is zero water now. That's how hot it got. Nitrogen is only at 1%. But CO2 is at 98%. And at 98% CO2, the atmosphere of the planet Venus is way too hot for any life on Earth to live on it. But we look at Mars, CO2 is 96%. And oxygen gas is 2.5. There's a little more oxygen on Mars, still not enough for us. Nitrogen is about 2.5. Again, a little more in Venus, but look at the difference between Mars and Venus and Earth. And water is anywhere from 0 to 0.1, because it has some frozen water at the polar ice caps, and there's some water that's underground that we can't really get to from here. We can see this stuff from telescopes. That's how we know the surface and the composition of the atmosphere. So when you're looking at this, guys, the key is think about Earth and think about how different the Earth is because life existed. Life in the form of those things that everybody's trying to kill all the time. Those things called prokaryotes, which are what?
Bacteria.
That's right, bacteria. And archaebacteria, don't forget archaebacteria, right? So prokaryotes did this. They prepared life for us, the planet for us. So that wasn't the end of the story. So you have this planet that's sitting in this solar system. You have this planet Earth that's sitting in the solar system. So you got water now. You have some bacteria living. Not many, but it's there. It's giant sun. Little moon. Cache, let's stay after class and let's talk. We have to figure out what to do. All right, so what happened to this planet during this time? As life was starting, the atmosphere was starting to change. Life hadn't started yet, but the atmosphere, the surface of the Earth had cooled down. We have a little more water. What brought water to our planet? What changes were happening during this early Earth time? Besides the volcanoes and the plates and everything, after the two planets collided and you had the moon, yeah?
Meteorites seeding the Earth with amino acids.
That's right. So we had comets and meteorites bringing amino acids and fats and some sugars, alcohols, all of the Earth. They bombarded the Earth. The Earth was bombarded with everything, all the what? All the monomers of life, right? Everything you needed, all the monomers of life. Not a pretty story. This planet that survived so much gets bombarded through this, it was in the movie, all this bombarding of these asteroids and comets hitting the planet, right? Bringing in water, some of the water was already here, and then bringing in more water and amino acids and alcohols, all the components of life. And then chemistry took over. Once you got all these things in the right conditions, somebody was making soup, weren't they? You ever make soup? You get the carrots, chop them up, put them in there, a little salt, a little pepper, some flavoring, maybe some noodles, little chicken, pieces of chicken, strip that chicken down, throw it in there.
Just a question on the few answer that.
Chicken soup, man. It's delicious stuff. And so somebody in the universe, or the universe itself, or whatever you believe in, nature, whatever, magic, whoever, go sit down. Somebody came up with this soup formula, and through all these little beads of the components, or something, or nature, or random, it happened randomly, right? Whatever, all right? These particles coming from all over the solar system started bringing these giant rocks, started bringing all the components of life together. And as soon as it hit the water, what did this thing start to make? Life. What was the first life?
Bacteria.
But what did it make before you got life? What had to be formed? That thing we studied so hard. A cell, which means you had to have what? Lipid membranes. And they form themselves, don't they? They don't need any help.
They spawn spontaneously.
They form spontaneously as long as they're in water and under the right conditions. You mix them up, they will form a bilipid layer, right? We know that now.
I got a question.
Hold on a second. We only got so far. It's all in the PDF, it's on the movie. I'm reviewing this with you. Tomorrow's a test, so make sure you're studying. Make sure you're watching those movies. Make sure if you need to remake the test, make up that, get your remediation for the test. You better come and get it. So you have these bilayers that make prokaryotes, and that's the beginning of life. And tomorrow you'll have a test on this stuff. Make sure you're ready. Goodbye.
That too?
Yeah, everything. This is all in the movie. This is all in what movie she says. After this, you have the prokaryote. The simple, yes, the DNA came as well. You have that's the idea of the formation of first life on Earth. We're prokaryotes. Please remember that prokaryotes were on Earth longer than any other. Any other organism. All right, they're the oldest of us. I'm recording now. So the prokaryotes have been on Earth for the longest, longer than any other group of organisms. We know that cyanobacteria, that the prokaryotes changed the atmosphere, right? And I've said it before, I'll say it again. Make sure you know the composition of the atmosphere before in early Earth and in the modern times. Make sure you know the composition of the atmosphere both in the early Earth and now. Okay? You don't have to know the composition of the atmosphere on Mars or Venus, but you do have to know the composition of the atmosphere on Earth. So make sure you're able to do that. All right, so that's prokaryotes, but did we talk about, help me out here, did we talk about in this class how we came to eukaryotes, how mitochondria and chloroplasts became incorporated into a eukaryotic cell? No. Okay, so what that process is called, the theory that explains it. Let me give you some facts, and let me give you then the theory that tries to explain these, all right? The observations are as follows. When we look at mitochondria, and chloroplasts, when you look at mitochondria and chloroplasts, what we find is that they have double membranes. They have two membranes. Their DNA, obviously, they have circular DNA. They have their own DNA. No other organelle has that. Mitochondria and chloroplasts. They have their own DNA. And their ribosomes are small ribosomes. They have their own DNA. It's circular. And as a double membrane. The small ribosomes are like prokaryotes. And the circular DNA is like prokaryotes. And double membrane is not like prokaryotes at all, no. But then on top of that, in the DNA, some genes, guess what? Some genes, guess what? No guesses? Like prokaryotes, that's right. So, a theory was composed that explains this. The theory is as follows. It's called endosymbiosis. Endo means within, and symbiosis means close relationship. Is that okay? Endosymbiosis. Is this okay?
What? You said endosymbiosis.
Endosymbiosis. Endo means within, Symbiosis means close relationship. I'll explain to you what this is. But do you understand those terms? All right, so let's see if at the end of this little mini story you see where the word endosymbiosis comes from and why it's important. So initially you had these bacteria, right? Some of them were very successful at making ATP. All right. Then you have this cell is bigger. Maybe it had some membrane-bound stuff. Maybe it even had some DNA inside a nucleus. Maybe you had even a nucleus and some DNA inside. I say maybe because we really don't know. All right. There's some of this is guess. And so you have this big cell, and there's evidence for this. We have all kinds of evidence suggesting this. In other words, we look at what goes on today, and we see some of these very same things happening today. All right? So this big cell, let's assume that they met in the wild, and the big cell is going to try to do what to the little cell? Devour it, is correct. That's how the big cell gets its stuff. The big cell is really good at getting resources. Also at not dying, right? It's not getting devoured because it's big. The smaller prokaryote's really good at making ATP, right? So they each have their own advantage. So I'm going to make the membrane of the big cell yellow, if you don't mind. So we have this yellow membrane, and then this little bacteria that's really good at making ATP. This is 1 billion or so years ago, right? A very long time ago, let's just say that. It goes through phagocytosis. Remember we went through that, what phagocytosis is, right?
No.
Yes, we did, but okay. Phagocytosis is when the cell envelops, circles, surrounds its food, and pinches it off into a membrane-bound organelle. Yes, we did. It's okay. You don't remember it, but you did. Phagocytosis is the process in which a cell, as you see here, starts to fold its membrane, its cytoskeleton bends, changes its form in order to engulf a larger object that could pass through the pores, the proteins in the membrane, or go through diffusion. This is the process, this is how a cell can take in a fairly large object. You notice the membrane surrounds the prokaryote, and as it surrounds it, the membrane becomes bends and surrounds the bacteria and becomes almost a second membrane. So as you see, there's a second membrane here surrounding the membrane of the prokaryote that was swallowed up. That explains a method a way in which an organelle could have two separate membranes surrounding it. How do you get two individual membranes surrounding one set of content? And this is one way you can get absorbed. You get phagocytosed, and inside this vesicle membrane that used to be part of the plasma membrane of the cell, right? Now is this a second membrane for this prokaryote. Now, interestingly, for some reason or another, this prokaryote was not digested, and in fact, as it moved on over time, it became part of the cell. It became an organelle in its own right. And as you know by now, the organelle is the mitochondria. Now you might ask, well, wait a minute, and someone did ask, well, how does it divide with the cell? You know, if it divides, if the cell is going to divide, what happens to that mitochondria? Well, somehow in the past, and again, this is all conjecture. This is an explanation of the facts. It's the best one we have, so we're going to go with it, and it fits all the evidence. And there's tons of evidence. It's not just, you know, that the fact that there's circular DNA in the mitochondria, not just that there's a double membrane, not just that there's small ribosomes that are like that of prokaryotes, but the genes themselves in the mitochondria are similar to some of the genes found in prokaryotes. So when we're looking at the evidence, it's pretty strong that this is one very good possibility that mitochondria used to be prokaryotes that were engulfed by one of the original cells in that primordial soup, and then as time went on through the process of evolution, that individual prokaryote became an organelle. Now, what did that prokaryote do? Well, it was sitting there, and then this cell starts to divide and make more. Well, it's not done. It's not dead, so it's also going to divide. It's receiving food as this cell receives food. It shares. It's a symbiotic relationship, and it's a commensalistic one. So this cell shares food with the prokaryote. The prokaryote shares ATP back, and they have this mutually beneficial relationship, right? Mutualistic relationship, I should have said, not commensalistic. all other cells that were eukaryotes, from the first eukaryotic cell, from that first eukaryotic cell, you came up, that eukaryotic cell did endosymbiosis again. It had a mitochondria. But then it came along something that could do something really interesting. What could this prokaryote do? What could this green prokaryote do? Say what? Absorb energy from the sun is right. So this thing can do something very interesting called photosynthesis. These things are going wild. They were going wild. They changed the atmosphere of the planet, and these highly effective ATPs were already ATP making bacteria were already incorporated. Maybe they were already organelles. Maybe they were still doing a symbiotic relationship. Whatever was going on, we're not quite sure. This cell came along, and then this first eukaryote came along and tried to and tried to eat this photosynthesizing bacteria. And again, looking at it time-wise, the cell then engulfed it through phagocytosis. I'm sorry that you're so immature that you can't handle a word that sounds like a bad word. What? So you have now you have this new cell, this new organelle that we call what? Chloroplast. So now this eukaryotic cell became the first what cell? Plant-like, right? The first progenitor plant. This one over here, before, so there were two, one of these went this way, the other one made what? Was, as it evolved over time. That's right, you said it right. You should say it openly. This one, in one sense, was the first, became the cell that became animal cells, as it developed multicellular life, right? Animal cells. It also became what? What else could it become? Yeast or fungus? That's right, somebody said it over here. Or protease. So animal cells, yeast, fungi, protease all came from this cell that did not have the chloroplast. It didn't take in the chloroplast, right? Because they're not photosynthesizing. So what you're left with is a group of photosynthesizing bacteria, like we say cyanobacteria or algae, and then you have plants. Those are the two things that do photosynthesis, because those are the two things that evolved over time. Everything else evolved from this cell that did take in the mitochondria, that does have a double membrane, but what it did not do is absorb. It does not absorb light. Does not do photosynthesis. All right. Question? Yeah, go ahead.
So, in other words, plant cells.
No, plant cells came. See, this is going to be important verbiage throughout your study of biology. Plant cells came from a similar common ancestor, right? So we all had one common ancestor. Plant cells, animal cells, and in fact, you can find genes in a plant cell that we share with them. There are genes in a plant cell. You can find that gene in you. In fact, you can find a mitochondria in plant cells. You can find a mitochondria in you. Why? How is that explained? Through the theory of evolution. And that's that, and in this case, endosymbiosis, and that's that we all came from a common ancestor. That doesn't mean that we came from plants. It doesn't mean we came from apes. It means there was this common ancestor that we both shared, that we got some of those characteristics. We share those characteristics with apes, and we share those characteristics with plants. Yeah. Huh? This would be the common ancestor here, right? Because as this cell divided, one cell went this way, right, and became protease, animal cells, and yeast. The other cell went this way and ended up eating a photosynthetic bacteria and then becoming the first plant-like cell. Are we good with that? All right. So the last little bit is this idea of cell theory. And cell theory is, it just says three things. Everything all known living things are made of cells. Bless you. A lot of people made it. Theodor Schwann and Matthias Schleiden were two of the people that helped develop it. Two, the cell is a structural or functional unit of all living things. All cells come from pre-existing cells. This is a key one. All cells come... Jeez. Pre-existing cells. So the cell, if you have a cell, it came from another living cell. Cells contain heredity information. All cells come from other cells. They can come from other cells through what we call asexual division, or they can come from cells through sexual division. But all cells come from other cells. 5, all cells are basically the same chemical composition. So that means that what? All cells have phospholipids, all cells have DNA, all cells have RNA, right? All right. 6, all energy of life occurs, all energy flow. This is an important one here. Oh, they're all important. The metabolism someone brought up earlier, the biochemistry of life occurs within cells. So these are really big ideas. You need to make sure you know them. This is cell theory. Everything that we talk about from now till the end of the quarter is going to be based on this idea of cell theory. All right, so there's 2 packets. Let me say this very clearly. I'm recording this so that, and I'm sending this out right before. Don't put anything away. Listen to what I'm saying. You're wasting time. I only got a minute left. I'm going to send this video out now. There'll be another video that's going to describe the directions for these. There's directions on the packets themselves. You need to find a partner in this classroom or in the 9th grade that has one of these, and you need to partner up with them. If you don't have a partner, you can do it by yourself. Hear me? You're just going to have to do both parts of the Dragon Genetics. Because the Dragon Genetics is asking you to find a mate for your baby. You're gonna make a baby, and you're gonna have to find a mate for your dragon baby, and you're gonna make a new baby. Do you understand that? If you don't have a partner, you're gonna have to make up your own. You have to make up 2 dragons. All right, take one of each and leave.